Hello, welcome if you're here. It'll be great to hear from people in the chat. Hopefully that's now live. We've just started up an A-level web class today. We're going to be looking at transformations of graphs and functions, which is hopefully something you guys have maybe met before at GCSE, but it's a really big topic and part of the pure maths. So yeah, we're going to get started pretty much straight away. If you've got any questions or comments throughout, please do ask in the chat and we'll go through some worked examples as well. Cool. I'm going to share the screen now, so hopefully we'll be able to see some of the slides appearing very soon. Let's make sure that's clear for everyone. Excellent. Welcome if you've just joined. Please do say hi in the chat. We're literally just getting started. So we're looking at graph transformations today, which is a massive part of the pure maths side of the course. Many of you would have seen it at GCSE. It sort of comes up throughout year 12 and 13. It's crucial for modelling as well. So it's in the pure, but it could appear in the applied, I suppose, in different ways. It's just a very key skill. So as I said, please say hi in the chat. If you've got any questions, any comments as we go, do share those with us. We're going to get started now, though. So welcome to everyone, and thank you for attending, especially on a Sunday. Here we go. So we'll get started. So I'm Max. I'm the kind of lead maths teacher at Snap Provise, and I did a maths degree a few years ago now, and I've been teaching A-level maths and GCSE for the past sort of 6-7 years now. As I said, let me know if you've got any questions or comments throughout. We're going to start looking at transformations today. So also let me know if this is a topic you're familiar with. We're going to look at a few examples and some past paper style questions as well. Right, I think let's get started. Here we go. So we're going to look at the shape of reciprocal and exponential graphs. And we're also going to look at how to apply transformations to these graphs. We'll also look at asymptotes and kind of key features. We're not going to do polynomial or modulus graphs. So let me know if this is something you've done before, and we'll get started now. Here we go. So just some typical examples. We might have, say, for example, a parabola, and it could be reflected and translated, but they would be sort of graph transformations. So hopefully we recognize the notation, but stuff like this is what we would consider a translation, like a shift. We should be familiar with scaling and how this works, and we'll apply this to some of the A-level graphs today. And also reflections, where this sort of negative scale factor comes into play. Okay, so as I said, do comment, do let me know if this is something you've done before, and also if you've got any questions, please share them with us as well. So transformations, this is a key on all of the different examples. This is a key part of the course. So all A-levels will involve this skill. And we're going to start by looking at reciprocal graphs. So here we go, nice example to begin. So the simplest reciprocal function is something like 1 over x. And that's sort of shown here. Who has seen this one before? Who's familiar with this? I'm just going to go over the axes because they're actually quite important lines. So for the graph of 1 over x, does anyone know what we call the x and y axis? The lines that it's sort of infinitely approaching but never touches. So these sort of lines, if you extend them, it gets closer and closer to, but never actually touches. There's a key name for these lines. They're a really defining feature of reciprocal graphs. So the x-axis is one, the y-axis is one as well, and it's a line that the graph is infinitely approaching but never touches, and it has a sort of very special name beginning with A. So this is called an asymptote. and it's a key feature we'll need to see on these graphs. So in the graph of this function, the x and y axes are, as we said, asymptotes. And you may have seen this graph at GCSE, but not really explored it in too much depth. So these are lines whereby the graph gets closer and closer to but never touches, never reaches, just infinitely approaching. There we go. Cool. So that's great if you've seen that before, but they're a really defining feature of reciprocal graphs, and therefore very important when we come on to transform these graphs, because we kind of need to know what happens to the asymptotes. So for example, if you're transforming parabolas like quadratic graphs, the key feature is often the turning point, the minimum or the maximum, and we can look at where that moves to, and everything sort of builds around that. For reciprocal graphs, we can really look at where the asymptotes move to, if we shift it, if we translate, if we reflect. So this is really important. Here we are. To start with, we're going to look at applying translations to reciprocal graphs. So hopefully we recognize translations were, these kind of things, where we add or subtract in the function or outside of the function. So the way to use this is to imagine the 1/x graph that we have in front of us here. Imagine that is f of x. What kind of transformation are we doing here? So the original function we want to compare to is 1/x. If I have 1/x plus 1, how would I think of that in terms of f of x? So the original function did the reciprocal, it put 1 over it, it sort of flipped it. So if I've got 1/x plus 1, that's like changing the innermost part to x plus 1. And then we can recognize this as a translation to the left by 1 unit. So an easy way to sketch this on here is to move all the individual points 1 unit to the left. And notice that 2 boxes on this graph is 1 unit. So I'm going to move it all to the left. Every single coordinate moves to the left. But also, another really important thing is that the asymptote, the key defining feature, will also move to the left by 1. So instead of being the y-axis, it's now the line x equals -1. So if I draw that in, that can sort of help to pin the graph in its position. So here we go. Now vertically, it's not moved up or down. It has just moved 1 to the left. So that f of x, that original graph, 1/x, has slid along to the left by 1 unit. And that's how we can understand how to draw this graph without having to do a table of values, without having to plot loads of points. We can actually acknowledge it as a shift of a graph we already know. And this is really kind of a key A-level skill. So that's great if you know about that, if you followed that. Let's have a look at this one then, because this is easily kind of confusable with the one we just did. So 1/x plus 1, this time the plus 1 is outside of the function. So this is like the function that we had, as shown on the graph here, plus 1 unit to all the y values. So essentially it's been moved up by 1 unit. And again, we could do it in a very similar way. We could take individual points and move them up by 1 unit. And then also, that is then going to transform, again, an asymptote will also move, and this time it will be the x-axis. So instead of being the line y equals 0, the line y equals 1 is now the new defining feature. It's the new asymptote. That asymptote has moved up by 1 as well. So let's fit that graph to that shape, see what we've got. So this is a translation of the graph we had, 1 unit upwards. It hasn't moved left or right, it's simply moved upwards. So the y-axis is still an asymptote. Okay, so that's how we'd use our kind of GCSE knowledge and understanding of transformation of functions to apply them to this new shape or this particular graph that we're dealing with here. Okay, right, let's move on. So now we're going to look at some scaling. So this is another way of transforming graphs. And this one, we can think of it as f of 2x, which hopefully we recognize as a kind of squash or compression in the x direction by a factor of a half. So the way I always teach it at GCSE is inside the brackets, do the opposite to x. Do we recognize that as a thing? So if we've got this graph and we compress it, the x coordinates effectively half, so it sort of squashes it in. So let's do that. Here we go. I'm going to half the x positions. And so this will squash the graph in. The asymptotes will still be the same. It's the individual points that will have sort of become closer to the axes in the x direction. So this is a scaling by a factor of a half in the x coordinates. So let me know if you've got any questions or comments, or if you've done this before, how you sort of feel with this topic. We will look at some exam style questions as well. This one, if we think of as 2f of x, this is now a scale or a multiplier by a factor of 2 to the y values. So this is going to stretch the graph this way by a factor of 2. So again, we can take the individual y coordinates and double them so that they sort of become doubly splayed out vertically. And so the graph will move in this way. The asymptotes will still actually be the same. They will still eventually tend to the axes. It's just the individual points that have got a little bit more stretched out. Okay, oh, that wasn't very well drawn. Let's try that again. Okay. So again, hopefully a type of transformation we've seen, but we can now apply it to reciprocal graphs. Okay, as I said, do feel free to comment, to ask any questions, to answer questions as we go. We're going to do reflections next, and then we'll look at a few exam style questions and introduce this skill to other graphs as well. Here we go. So this time, can anyone suggest what transformation we've got here? Again, if I'm looking at the original graphs as f of x being 1 over x, what have we done to it? If this is f of x, what's this effectively? What has happened here? How have we done this one? So if this was f of x, what have we got going on here? It's 1 over minus x. So if we have any suggestions, please let me know. But how have we transformed this graph? Well, this time the minus is in the denominator. It's in the sort of reciprocal part of the function. So it's kind of happened within the function. So this is now a reflection, and it's actually a reflection in the y-axis. Sorry, the y-axis, because the x value here that's at 2 would now go over here at minus 2. So we're sort of reflecting around this axis. And likewise down here, the x values are taking sort of negative versions of themselves, and we get this image. Now this one here, we can think of as minus f of x. So this time we're timesing the y values by -1 and effectively reflecting up through the x-axis. So the positive y values are becoming negative and the negative y values are becoming positive. So this point would go to here, this point would go to here, and that bit would be reflected up. And then this part would be reflected down. And so the net effect is the same for this kind of graph, where how we view it is up to us, but it actually is effectively the same type of function for this particular thing. That doesn't always happen. We have got to be careful with what type of functions that happens with. Hello, welcome if you've just joined. Please do feel free to ask any questions, comment, or any answers and stuff if you need to. We've just looked at a few graph transformations for the reciprocal graph 1/x. So we started with a shift, translations, we've got on to scaling, so stretching them, and then we've looked at reflections as well. So we're now going to move on. Let's have a little look at the following. And we're going to look at this one. Now, I don't remember learning about this function before A-levels. I do remember it during my A-levels. I don't remember it at GCSE. So I think this is quite new for a lot of people in year 12. So this is actually a reciprocal square function. And the simplest scenario is actually 1/x squared. And it kind of is like a transformation of 1/x because everything is positive. All the y values are positive for this type of graph because when we square something, it's positive. So the x and y axes are still what we call asymptotes. The lines that they infinitely approach but never touch. And the graph will always be, for this type of one, above the x-axis, as we said. So let's have a little look. We'll do a little checkpoint, and now we're going to look at some exam, like past paper questions. Then we'll push on to exponentials and a few other things as well. So here we go. If you want to let me know in the chat, just a little indication of how you found that content. We've introduced reciprocal square functions as well, and then we'll do a little bit of exam practice. So let me know, just a 1, 2, or a 3 on how you're feeling with that sort of content. It might be something you're really familiar with. And then let's have a little look. Here we go. So this one, sketching this graph here. Well, I appreciate, okay, no worries. So if we're a little bit unsure, do feel free to ask any specific questions. I'm happy to return to any slides. We'll do some consolidation now, though, through some past paper kind of style questions. So thank you for sharing comments. If you do want to ask any specific questions, please do. So now that we know the graph of 1/x squared has that shape, because we've got a minus in the front, remember that this is a reflection and the y values are made negative. So it's basically a reflection in the x-axis. A bit like how x squared minus x squared sort of goes the unhappy way round. So we've just reflected a known graph shape down in the x-axis because what we've done is we've changed the y coordinates from a positive version to the negative. So imagine if ordinarily the coordinate's up at 4, then I times by a minus, I turn it to -4. I've effectively brought all those coordinates down from the positive place where they existed before to now being below the x-axis. Okay, so this really is directly off the back of the graph we just saw. It's reflecting that graph, the x-axis, turning all the y values, all the outputs negative. And that's the shape we would get. And this is the other thing that I think a lot of students at A-level maybe panic with or get a little bit put off of this topic, is it is just a sketch. So the skill they're testing is that basically you know and you understand and you appreciate the shape of the graph and the key features of it. You're not supposed to be a computer or a robot or plotting it like a GCSE where you're doing a dot to dot thing. You're just supposed to know I understand it would be that shape, but it now reflects like this. So it's more of a general appreciation for the type of function that we've got. And that's what we're trying to display to the examiner and show them that we know that. So this next one, this is all graph transformations. And it's just a little extension on the one we've just done. We've just seen that minus 1 over x squared looks like this. So adding the 3 on does what to it? What will that do to this graph? What transformation has happened? We've sort of added a transformation in now to take this graph somewhere else. So 3 minus 1 over x squared, which is the same as minus 1 over x squared plus 3. The plus 3 has happened outside of the function. So this is a translation vertically by 3. So it effectively just moves this graph upwards by 3. Very close. Okay. You are absolutely right. That's a really good suggestion, and I'm going to talk about that. It is a translation of 3 units. Yes, vertically. So it will look like this. So I'll show you how the one we suggested would be written, because they are so easy to confuse. But thank you for that suggestion. It's up here. Yes, the asymptote moves up by 3. If we wanted to move it 3 units to the left, that would be something like this. But very easy to mix that up. That's why we're going through it. So thank you for that. Absolutely right. It is a translation of the graph we just saw, but it's upwards. And I think it's actually helpful personally if I see it written like this. Like, I like to think of that on its own after, but that is effectively the same thing. So brilliant. Thank you for the comments there. And this is good. This is really good to see how it would come up in an exam. Right. The next one isn't even a sketch. It is literally just a 1 mark quick answer. This curve that we drew previously has been stretched parallel to the y-axis with a scale factor of 2. State the equation of the transformed curve. Can anyone do that? What do we reckon? So we're stretching this by a factor of 2 vertically. So we're kind of affecting the y direction. So this vertically stretched by a factor of 2, we need to suggest an equation that does that. So this would be something like yeah, superb, excellent. Thank you for the suggestion. That's absolutely spot on. So you've basically done minus 1 over x squared times 2. And people at A level do get a little bit shaky with this because they think, if I times it by 2, where do I put the 2? Do I put it out front? Well, if you times a fraction by 2, you're effectively timesing the numerator. Like if I have 1/5 and I times it by 2, I have 2/5. And I know that sounds like a very basic thing to say, but that is exactly how you'd write it. So very well done. Thank you for the comment there. That was lovely. Right, we're going to push on, but really well done. That was great. Now we're going to look at this skill applied to exponential graphs. So who here has seen an exponential shape before? Who knows what it looks like? So an exponential graph. I think this is very new a lot of the time at A level. This is something sort of the form a to the x, something to the power of x. Now, I'm going to start with the graph of 1 to the x, 1 to the power of anything, 1 to the 1, 1 to the 2, 1 cubed, 1 is all 1. So 1 to the x actually is just another way of writing the line y equals 1. Okay, that's what the line y equals 1 to the x looks like. Okay, this is just a horizontal straight line. So what we're talking about is as soon as the number is above 1, it takes off in this greater than 1. It takes off in this exponential way, this very explosive, quickly growing way. But whatever that base number is, whether it's 2 to the x, 3 to the x, 4.5 to the x, whatever it is, the y-intercept will always be what? Imagine it was 5 to the x and x was this value here, 0. We want the y-intercept. Excellent, really good. The y-intercept will always be 0, 1. That's superb. So that is a key defining feature of these graphs, whereby they are all almost like pinned into position at 0, 1. The individual steepnesses are transformed based on the base. But absolutely right, that's brilliant. That 0.01 is always going to be the y-intercept of something of this sort of form. Very good. And that will be a kind of key mark in the exam mark scheme, that you know that position. It's so crucial. And then negative powers will produce fractional answers. So you'll have an asymptote here of the x-axis, and then it sort of takes off rapidly, ever increasing after that point. So they're cool graphs to know and understand. And again, it's about appreciating their shape. Very good, excellent. So let's look at transforming them now. We're going to try and apply those skills of graph transformations to this situation. So again, I've given you the graph of a to the x. And we now want to sketch a to the x plus 1. So the plus 1 is in the sort of exponential bit. So hopefully we're happy that this is effectively this kind of transformation. If we can treat this as f of x, this is f of x plus 1. So what's this going to do to that picture? That looks like that, goes through all of those points, and I'm going to do f of x plus 1 to it. What's going to happen to this image, to this thing we can see in front of us? What does this do? It is a translation, but let's be specific. So inside the brackets, you do the opposite to x. So this will be a shift of that graph to the left by 1. Yeah, so let's have a little look. So I'll sketch this. And again, I'm just going to do it point by point. There we go. The individual points are just going to move across. So it's the same graph, basically just sort of slid to the left. So now it will go through here, and it will still have the same asymptote. Brilliant. Now this one, a little bit different. What kind of translation is this? That was our f of x. What's happening now? What would we do with this one? What does this do to that graph? What do you think? So it's another shift, it's another translation. Yes, brilliant. And maybe that's something I should have explained a little bit more carefully earlier, because that's sort of something we've seen before. Inside the brackets, you kind of do the opposite to x. So if it's plus, you minus it, but it's always horizontal in the brackets. Superb question. That's a really important point to clarify. So if it's half the x values and squash it, but it affects x inside the function. If it's outside of the function, it affects y. And the reason for that is because you're effectively doing the function and then doing something to its output, which is like the y value. So that's what the function is, plus 1. So we're just moving it up by 1. So because this is outside of the function, it affects y. So you're absolutely right. That was really important to pick up on. Inside the brackets, it affects it horizontally. So it affects x, but sort of in the other way to what you think. Whereas outside the brackets to y, it just does what you expect, but to y. So this plus is 1 to the y values. So it just moves the graph up vertically. So here we go. So actually, sorry, more specifically, that's going to move to there. The asymptote will move up as well. We've added 1 to all the coordinates. Let's try and get that a bit better. Does that make sense? So we'll do a couple more, but please do ask questions, or if you want me to go back to any, let me know. So that was a vertical translation by 1 unit. Very good. So let's keep going. So this one here, this one is a sort of scaling or stretch. Now let's think about it. This one is like f of 2x. It's inside the function. It's inside the exponential. Whereas this is doubled what the function was. So this is like on the outside. So here, it affects x, but instead of doubling it, we halve it, because inside the bracket you do the opposite to x. So it sort of squashes it that way by a factor of a half. So these points get halved. Now 0 getting halved is still 0, but these points sort of get compressed to half the values. So it kind of squashes it horizontally. Squashes the graph in. Okay. Okay, so hopefully everyone can still hear me. Now this one, this is being stretched vertically. Okay, so this one is being stretched by a factor of 2 vertically. So this point is actually up here. This point gets doubled. So it sort of rises doubly as fast. Okay. Right, so let's move on. Now, this is a little bit weird, this one. It's a really good one to do, actually, especially as we approach the exam practice of this. Any suggestions here, what we can do? We need to think of a little bit of index laws, indices, because this can throw a lot of people off. Again, we're dealing with f of x being the a to the x graph and thinking about how that's going to be used. So what would happen here with this one? How can we think of this? 1 over a to the x. If this here is f of x, this is a to the x, what transformation has effectively happened here? Think of how this could be written using powers. The -1. So this can also be written as a to the minus x. Yeah, really good. Exactly that. Now, hopefully we know that when we times power, like a power to a power, you times them. Superb suggestion in the chat. So because we can now rewrite it as this, which is really the big skill for this one, this was potentially a really tricky question, we can then think of this as f of minus x. So this is a type of reflection. Now what this means is, remember it affects x, and if you times the x values by a minus, what's going to happen is they sort of reflect around the y-axis, because when this was 1, it's now -1. This value here that was -1 is now at +1. So what happens is it reflects around the y-axis. And that's what that would be. Brilliant. Whereas this one, this is like minus f of x. So you're timesing the y values by -1 and therefore reflecting them in the x-axis. The point that was up at 0, 1 is now at 0, -1. This point that was at 0, 2 is now at 0, -2, and so on. And so what we have is we end up having a reflection in the x-axis, but it's the y coordinates it's affected because it's out of the brackets. That's what throws people off, I think, when they hear, oh, it's a reflection in the x-axis. Yes, but what you've done is you changed the y vertically. So they're both reflections. This was the harder one to recognize. So very well done if you get that. That's brilliant. That's lovely to hear. And if there are any questions we need to tease out, because we want to basically be able to apply this skill to any graph. If I present you with a graph and you think, well, it's very similar to that one, but it must have just been shifted or reflected, then we can actually sketch graphs really well. So for example, if you have x squared and then you have x squared plus 1, it's just that graph moved up by 1. It's just transformed. So being able to recognize this, that's great. That's great that hopefully this is useful, but it is such an important skill, and it's one that people underestimate. They think, well, it's not something you can really blag. You have to know what's going on in the exam questions. So really a little checkpoint, and then we'll do some exam style questions of exactly what we just did. And if anyone wants to ask anything or wants to go back to any of the previous slides, please let me know. So yeah, just give me a 1, 2, or a 3 on how you feel with this content. Thank you for the comments and the questions as we've gone throughout, because that's really useful to understand exactly what needs clarified and stuff. So this is, as I said, a really important topic, and it's worth taking the time to review little bits. Even if you want to see one of the slides again, please let me know. So yeah, just a 1, 2, or a 3 if you want to give me a little checkpoint of how you feel with that. Yes, absolutely. For the ones we just did, was that this one here? We wanted to revisit that one. Because we also did this, yeah, brilliant. Feel free to screenshot it. We've also got, we did one earlier with that same skill, but for reciprocals. Would you like me to re-show that one? So I can go back to the reciprocal one and show you that. Yeah, okay, so feel free, if you want to screenshot that, I'll quickly go to the previous skill, but for reciprocals, whereby we squashed it by a half and we stretched it by a factor of 2 vertically. And it's seeing that from this bit that is the skill. Once you know what transformations happened, you're just effectively drawing that on. You're just making that sketch happen. But it's interpreting that this is a stretch, this is a scale. It affects it horizontally. This one affects it vertically. So that's really good. So what do and if you do want to revisit at the end again, that's absolutely fine. Right, let's have a go at these questions here. So this is very much an exam version of what we're doing. So it says sketch the curve y equals 6 times 5 to the x, stating the coordinates of any points of intersection with the axes. Now, again, people panic. They think they need the calculator. They think they need a table of values. It doesn't say plot. It doesn't want you to draw this ridiculously accurately with loads of coordinates. It wants a sketch. It wants to know you understand the shape. So straight away, we should be thinking this is an exponential and it's transformed. So 5 to the x very quickly looks like that, goes through 0, 1. Okay, but this is 6 times 5 to the x. So this is like 6 f of x. So what's going to happen to this graph? So the 5 to the x shape that I've got in my head that has an asymptote at the x-axis and goes through 0, 1 and takes off like that. What happens to it if I times it by 6? I have that function, and then sort of externally to the outputs, I times them by 6. I times the outputs by 6. I times y by 6. So effectively, what have I done to that graph? I've taken it and I've scaled it vertically by a factor of 6. Yes, perfect, stretched it by 6. So all the ordinary kind of y value heights, outputs get times by 6. So eventually it will still approach 0. But instead of going through 0, 1, what's it going to now go through? So that's a key point to make a note of. As it does say, stating the coordinates of points of intersections with the axes, I'm going to go 6 because I've times that 0, 1 point by 6. So the graph has got sort of 6 times steeper or taller. And we don't need to draw the other one on there. We don't need to draw 5 to the x. It's just asked us to sketch this. What they did want us to show, which was really important, is that we recognize where it intersects the axes. Does that make sense? Why it goes through 0, 6? Is that clear? So the ordinary 0, 1 has been times by 6, so that will move it up. However, the asymptote at 0 times by 6 isn't going to move. Brilliant, excellent. Thank you. So the next one, this one here, is actually, this is a really similar question, and I would argue they wouldn't be worth these kind of marks. This is effectively the same thing. K to the x is still that shape. So 4k to the x is effectively the same. It's asking us to do that. So what's the y-intercept here? I'm going to draw the very generic shape. I'm in control of the scale. So what coordinate is it going to go through? Anything to the 0 is 1, times it by 4. It's going to go through 0, 4. Okay. So hopefully that was all nice and clear. Now these questions, obviously, this is very much a skill for pure maths that will evolve in year 13 as well. And the more graphs you learn, the more we've got to be able to take it back to this and apply these transformations. So we've looked at the shapes of reciprocals and exponentials, we've applied transformations, and we've looked at asymptotes as well. If there's anything you guys would like to go back over, any questions you've got, please feel free to ask. I think it was really good to see it in light of exam questions as well. So a sketch, as I said, is very much the A-level skill. We're not generally asked to plot as much, we're asked to sketch, which people mistakenly think that means you can just be really, not rubbish, but like do a rough version and just sketch it, and it's not as important. It's actually more important in demonstrating you know intuitively how the graph looks. It's not a case of I need to be super robotic and draw it like a computer would. It's more a case of I appreciate the shape, I know where the turning points are, I know where the asymptotes are, and I know where it hits the axes. And then the table of value stuff is a little bit irrelevant because you understand how the graph looks. So that was really good there, and thank you for all the comments and answers throughout that. If there's anything anyone wants to ask me or revisit, or wants me to go back to, please let me know. But these are really typical year 12 pure maths questions and topics, particularly this graph here. This is the one I know for a fact I had never seen before A-levels. I hadn't seen it at GCSE. I'd seen the reciprocal graphs, I'd seen that shape, I'd seen an exponential shape. I didn't really maybe understand all the features, but this I hadn't really covered. Now, if you produced a table of values, you would of course get that graph and you could plot it, but it's really handy if we actually know and understand how that should look. So it behaves a little bit like a modulus in a way that it all gets turned positive. So it still has asymptotes at the axes, but the negative values get reflected up and turned positive because of the squaring process. So that graph is a bit more new to people. Brilliant. Right. So really well done. As I said, if there's any questions, let us know. Absolute pleasure working with you all today. I think hopefully that was useful. And it's been lovely to see the comments and the questions in the chat. And I appreciate that on a Sunday as well, doing difficult pure maths content. So really well done. But yeah, if you have any questions, let me know. As I said, very grateful to everyone that shared comments, questions throughout today. These sessions are running on Sundays going forward, so there's other subjects as well. The sciences will also be running web classes. But as I said, really appreciate you all taking part. Hopefully that was useful. And yeah, hopefully see you at the web class very soon. That was really good. Brilliant. So well done, everyone. I think I'm going to stop sharing that there. No worries. Thank you as well. Thanks for all the questions and comments. Have a good rest of the day and have a good week as well. Hopefully see you at a web class soon. Take care, guys. Very well done. Thanks.